Hi everyone. So today we're just going to get a little introduction and a little bit of background about, I'm going to call it a sense of scale. So that is to say significant figures, scientific notation, units, a little bit of back of the envelope calculations you'll see as we go on in today's lesson. So first, in dealing with measurements and significant figures, when you measure something, this is where significant figures actually shine. You might have used them kind of willy-nilly in previous classes, but the true meaning or true usage of significant figures is to tell you how precise a measurement is. Right? So the more significant figures your measurement has, the more precise it is. Right? And that is to say this precision is with only a certain level of detail. So let's say we have a ruler. Rulers, as a rule of thumb, have measurements within plus or minus 1 millimeter. So that's to say the precision of the ruler is 1 millimeter. Now you can have some stopwatches you may be using in class, or some nicer stopwatches probably here. They may have a precision of 0.001 seconds. All right, that's very precise. But because of reaction time, the measurement may be far less precise than that, on the order of even 1 second. So you have to be very careful with significant figures in that sense. Now, significant figures is going to help us with knowing what digit is reliably known. So for example, if you measure something and it has a length of 6.2 centimeters, then the 6 and 2 are both significant. That is to say, how precise this measurement is only to the, what's that called, the tens place in the decimal point. Anything after that is not reliably known, and therefore we do not record it as a significant figure. So just kind of applying this idea, so let's kind of pause and think here. So let's suppose we're dealing with a calculation, and 9 out of the 10 numbers that we're using in this calculation are known with a precision of 0.01%. That is very, very precisely known, at least in what we'll be dealing with. And let's suppose this 10th number in the calculation is poorly known, with a precision of only about 10%. Right? If you think you're doing some calculation with these numbers, how reliable, what is the maximum precision you think a result can have? All right, so pause this video, think about it a moment, and then you can hit play. All right, so hopefully you guys were thinking about it. You might have averaged out these precisions, but actually we only be as precise as the least precise number here, and that is 10%. So our final answer can only have a maximum precision of 10%. Now, some tactics or strategies or rules, if you want to say, when using significant figures, they're listed here. I'm just going to quickly go through them. If you're multiplying, dividing these numbers, you want to make sure that your final answer has the same number of significant figures as your least precisely known number in the calculation. Right, so if we're dealing with this example here of 3.73 times 5.7, that only has, the least precisely known has 2 significant figures. So our answer here is 21. When adding and subtracting numbers, we have to worry about the amount of decimal points we have. So our final answer should match the least precise value, which is going to be the smallest number of decimal places. Right, so 18.54 plus 106.6. The 106.6 is least precisely known with 1 decimal point, so our final answer can only be as precise as 1 decimal point, so 125.1. Also, exact numbers have no uncertainty, so therefore they do not change the number of sig figs. So for example, if we're dealing with the number pi, pi is exactly known, and so therefore it does not affect the number of sig figs. And if you're dealing with formulas, any numbers presented in formulas are also exact and do not affect the number of sig figs. The general exception to these rules is going to be when you're doing intermediate steps to calculations. In order to minimize round-off error, you want your final answer to be the proper number of sig figs. So a general rule of thumb is to go 1 significant figure extra during your calculations, and then at the end, round to the proper number of sig figs. Changing gears a little bit, talking about scientific notation. It's an easy way to write down long numbers, whether that be really large or really small. Now, I'm not actually going to go over how to do scientific notation. It seems like a lot of you guys already know this concept. So we're just going to breeze through this, skip this slide here, and this slide here. Moving on to units in general. Units are extremely, extremely important. Any other teacher that says otherwise, no, just no. Units help you understand what you're even talking about. So, for example, if you go to the deli and say you want 3/4 of cheese, what does that even mean? You could mean 3/4 of a wedge. You could mean 3/4 of a pound. You need to specify what you're talking about. This is especially true in physics. And what we'll be using in class is actually using what are called SI units. SI units actually comes from the French phrase here, and SI being Système International. And we're going to be using this rather than the units we may be using here in the United States. Royal units, or imperial, I guess is the right word. I'm sorry about that. Sorry for that typo. And we also call this metric system. So we'll be using the metric system. When it comes to these SI units, there are 3 basic quantities. These are time, length, or you can think of that as distance, and mass. Right? Basically, every single unit we deal with is going to be various multiplications and divisions of these units. Right? So actually here I have part of the AP formula sheet here for what units they give you. So they tell you M is meter, kg is kilogram, so on and so forth. And then all of these other variables that are not meters, kilograms, or seconds are actually all just manipulations of those 3 variables. When I say variables, I mean units. So for example, the Newton here, symbolized with a capital N, that's actually going to be kilogram multiplied by a meter divided by seconds squared. And we'll get more into that later, but just to give you a general idea. And we're going to be using SI prefixes as well. So this is going to be really great since scientists and physicists are lazy and we don't want to write in scientific notation if we don't have to, just because there's too much writing. And SI prefixes are very helpful for that. So what that basically means, you guys are actually probably very familiar with this already. We put this prefix in front of our word and it's going to change what factor we multiply this number by. So for example, if we're dealing with a kilogram, a kilo is an abbreviation for 10 to the 3rd power, or a factor of 1,000. So therefore 1 kilogram is going to be 1,000 grams. And we can do that to all types of units. So we actually use these symbols here to shorten. So rather than write, say for example, terabyte, we symbolize that with a capital T and we put that in front of our unit. So 1 MW is actually 1 megawatt. It's how it's pronounced, and that's equal to 10 to the power 6 watts, or 1 million watts. Unit conversions, I'm going to skip as well. I'm skipping this slide as well. All right. Reasonability is going to be something we look into a lot. So for example, can a bicycle go that fast? This is where unit conversions can be very helpful. So let's suppose we have a problem or we get a solution that states that a bicycle goes a speed of 20 feet per second. Great. Some people may understand what 20 feet per second really means. For me, I kind of like to think of things in miles per hour since that's what I'm used to. So why don't you pause this video, convert 20 feet per second to miles per hour to see if this is a reasonable speed. So hopefully, when your conversion, you found that you have a value of about 14 miles per hour. You can also write that as 14 mph. Right? And if you're riding a bike at 14 miles per hour, that seems pretty reasonable. So this is very useful because you might be dealing with a problem where instead of 20 feet per second, you might have gotten something like 100 feet per second, which I guess you can kind of think about, and that seems pretty unreasonable. But you could also do the calculation, convert it to miles per hour, and you see you have an unreasonable answer. Another concept that's going to be really helpful for us to determine whether something is reasonable is estimation, or what I like to call, or scientists like to call, back of the envelope calculations. So these are just very quick calculations to see what kind of sense of scale we have going on in our problem or in our experiment. And in dealing with this, there's actually many different ways you can do back of the envelope calculation. The reason why it's called that is just it basically means you're doing this calculation on a scrap piece of paper. It's not something you want to keep. It's just something very quick, very sudden, and just to get things done. Now, when you do an approximation, you can use the, oh geez, I don't even know what that's called. The tilde? I think it's a tilde. I don't know. One of my teachers in college called it a twiddle, which tilde. If you use one tilde, that means we have a very rough approximation, and that's even less precise than using the approximately equal symbol, right? So the equal sign, that's basically two tildes, right? All right, so just as a very quick, rough example here, you can estimate your height in the back of an envelope calculation. So kind of thinking about, let's say we're asked to say your height in meters. All right, so you can kind of think, well, is my height close to 1 meter or close to 10 meters? Very roughly. And hopefully you say that your height is closer to 1 meter. Even though that may be slightly small, it's the correct order of magnitude. If you said how your height was 10 meters tall, that's like 30 feet. That's way too large. This type of estimation, this back of the envelope calculation, is going to be much more useful and more practical when we're dealing with equations that have a lot of things being plugged in. And that'll allow us to see if even we wrote down the wrong equation, if our answer makes any sense, if we know our final answer would be just way too big or way too small, we know something went wrong. So that's what I have for you guys today. So have a nice night.